The monsoon clouds are low and laden with moisture. And as the currents rise, these are cooled down and cannot hold their moisture any longer. The subsidiary ranges like the Pir Panjal and the Dhauladhar that stand directly across these currents get an immense downpour of rain. But these outer ranges draw off only a portion of the enormous reservoir of water that is held by these clouds. And as the current rises and approaches the spurs and ridges of the great Himalayan range, they are cooled down further. These currents are stronger in the eastern Himalayas than in the west because that is the direction in which the monsoon approaches. Thus, their effect is much more pronounced in the east than in the west. And this results in a marked east-west precipitation gradient. Rain provides a considerable amount of the water resources that feed the main rivers of the Himalayas. Below 3,000 meters, the forests retain the moisture, provided that they have been left there standing to do so. And it is between the altitudes of 3,000 meters and 2,000 meters that springs emerge and feed the main streams. The denudation of catchment areas in many parts of the Himalayas causes increased water runoff, strips the soil of cover, causes landslides in gullies, and increases the chances of debilitating downstream floods in case of a cloudburst. It is the Himalayan glaciers, however, that are the enormous permanent reservoirs feeding the great rivers of the Indian subcontinent. Let us now see how these fantastic rivers of ice are formed. When snow falls on the high ridges, above 5,000 meters and up to 6,000 or 7,000 meters, or even more, it slides and avalanches down the crowning ridges into the valley immediately below the summit ridge. Here the snow gets slowly transformed to ice due to the immense pressures of fresh layers of snow crashing down from above. Now this vast sheet of ice cannot cling on to the steep slope on the face of the summit ridge. After lying, accumulating and increasing in size in this very precarious position for months on end, the hard ice below starts moving forward due to the pressure of the fresh falling snow. There comes a point when this vast storehouse of ice and snow breaks away from the ice fields on the surrounding slope, and this point is called Bergschund. A deep cleft becomes visible across the face of the mountain, and this is the birth of the glacier, as water commences its long journey down to the sea. It is below the Bergschund that the glacier proper starts. Pressure from behind the bergschrund starts the glacier moving, and then the constantly accumulating snow behind the bergschrund keeps the glacier moving. Thus starts the odyssey of the glacier to its melting point, where the liberated waters run free. Glaciers on the south side of the Great Himalayan Range reached their melting point at an average of about 13,700 feet above sea level. The rate of movement of glaciers varies, but the average for the Himalayas is around 6 centimeters for every 24 hours. Thus, nature provides the perfect mechanism for storing vast reservoirs of water and releasing them at a very controlled rate. The lengths of Himalayan glaciers vary considerably, with the world's largest non-Arctic glacier, the Siachen, reaching an amazing length of 75 kilometers. This is the Hanuman Tibba glacier, the primary source of Beas, and having a length of 7 kilometers. This means that the ice that has fallen on the glacier at its headwaters will journey for hundreds of years before reaching its melting point in the Beaskund plain. The Bara Shigri Glacier in Lahore is 28 kilometers long and nearly a kilometer wide at its mouth. Its millennia-old ice is black with age as it curves down from its source at the great circle of peaks. The Bara Shigri adds its waters to the Chandra River, which in turn has its source in the glacial masses of the awesome Mulkila Glacier. Parvati Valley, adjacent to the Kullu Valley, is home to almost 50 large and small glaciers. This is the terrain for adventurous trekkers and not run-of-the-mill tourists. Beyond Pulga, the Parvati Valley ascends southeastwards, meeting up with the Dibi Bokri Nala, a tumultuous torrent fed by the 4 glaciers at the head of the Dibi Bokri Basin, while the 6,000-meter summits of Rubalkhand and Kullu Makalu tower above. It is in the Garhwal Himalayas that we come across the true giants which give birth to some of the major rivers of India. The great Gangotri Glacier, the vast reservoir of ice that gives birth to the holy Ganga, is almost 40 kilometers long. Here's an interesting point. As is commonly believed, glaciers do not melt due to the sun's heat, but rather due to the pressure exerted by millions of tons of ice upon the lower layers of ice towards the bottom of the glacier, and also by the friction between the various layers of ice moving against each other that leads to the melting of the glacier. The Himalayan glaciers are an ever-renewing source of water. In summer and autumn, billions of cubics of water melt down from the glacial ice and sustain the rivers. An idea of the huge reservoirs of water that are held imprisoned by the glaciers can be had from the fact that a single giant glacier like the Gangotri has a volume of 20 cubic kilometers of ice. Now compare this to the reservoir capacity of the Bhakra Dam and the Gobind Sagar Lake, which has a capacity of less than 8 cubic kilometers. During the monsoons, water from the melting glacier adds to the water runoff, causing floods in the middle and lower valleys. A safety valve provided by Mother Nature to check the excess overflow of water from the glaciers are moraines. As the glacier starts its journey from the parent ice field in the Bergschund area, rocks and boulders get dislodged from the mountainside and pile on to the glacier. In its forward journey, the glacier takes along with it and bulldozes this huge mountain of rock and debris. The lateral and terminal moraines, as they are called, check the excess overflow of water and form lakes. You will be able to see hundreds of these lakes in the path of many of the Himalayan glaciers. Besides the great reservoir of water in the Himalayan glaciers, the rainwater falling on the forested slopes and valleys is held in the soil, emerging at different points as clear mountain streams. This capacity of the soil to retain the water is seriously affected by deforestation and the removal of the vegetative scrub cover. Soil becomes loose and tends to throw the water off, increasing surface erosion and soil instability. It is really a very vicious cycle, with the lessened capacity of the soil to hold water contributing largely to downstream floods during seasons of heavy precipitation. At other times, a drought-like condition persists, with the perennial springs drying up after being deprived of their catchment areas. The eastern Himalaya receives far more rain as a result of its positioning along the path of the monsoonal winds, and the lower latitude makes the climate even more tropical. This heavy rainfall has an explosive effect on mountain slopes in these regions, especially nowadays after the results of increasing deforestation are being felt. It becomes a vicious cycle with an ever-spiraling denudation rate. A good example is the Tista flowing through the Sikkim Himalaya, and possibly the wildest river in the entire Himalaya. The Tista has always been considered as a very wild and unpredictable river, with a valley extremely prone to cloudbursts, landslides, and flash floods. Thus, the Tista has the highest sediment yield of all Himalayan rivers, as well as one of the highest denudation rates. Simply stated, it means that the river is performing its appointed task of leveling the Himalayas with an efficiency far exceeding other, much bigger Himalayan rivers. Another major factor in the ruination of riparian zones is overgrazing by cattle and sheep. This form of degradation does not convert a forest into a stump field overnight, but slowly, insidiously, causes far-reaching and irreversible changes in the ecosystem. Over a generation, heavy grazing can remove the shrub and understory cover, vital for the existence of many rare animal and bird species. Thus it is that the Himalayas as Weathermaker work in unison with its inbuilt complex mechanism consisting of glaciers, ice fields, and the forested slopes. The shield provided by the Great Himalayan Range and its subsidiaries that stand across the path of the southeast and northwest monsoons is the primary factor in trapping and channeling the monsoon clouds to shed their floating reservoir in the form of rain. Then, the glaciers take over the job of keeping the water in stasis as ice and doling it out to a thirsty human race. Any detailed study of rainfall needs a dense network of observatories which do not exist in the Himalayan region due to difficult terrain and inaccessible areas. It is therefore not possible to correctly estimate rain or snowfall distribution accurately in most of the remote catchment areas. In the interior areas of the Yamuna catchment, there is not even one rain gauge for every 300 to 400 square kilometers of the catchment area as recommended by the World Meteorological Organization. In fact, Indian meteorologists believe that given the extreme variability of rainfall patterns due to the complicated lie of the land, the density of rain gauges should be one for every 150 square kilometers. Rainfall also varies with altitudes, it has been found, and the net result is that areas beyond the main Great Himalaya range, as well as those shielded by high ranges like the Pir Panjal, are rain shadow regions receiving very little rain. Thus, the Trans-Himalayan region tends to be cold, high-altitude deserts with a specially adapted flora and fauna. Kashmir Valley has its own, mostly self-contained weather system regulated by the large number of lakes in the basin. The monsoon clouds that do get across the Pir Panjal gives 1/4 the amount of rain that they give on the southern slopes. Western cyclonic disturbances are important weather factors in the Punjab Himalaya. For example, whenever a monsoon depression occurring over the Punjab Himalaya coincides with the passage of a western disturbance moving eastwards, exceptionally heavy rains occur in the Beas catchment. This happened again this year, causing widespread devastation in the upper Beas Valley, where the land, because of extensive deforestation, has lost its capacity to buffer such heavy rains. Immensely destructive flash floods are the usual result. So far we have seen how the Himalaya affect the monsoon clouds and consequently weather patterns all over northern India. Now we will take a look at how the Himalayas affect the very formation of the Indian monsoon in the distant waters of the Indian Ocean. Using computer simulations, scientists have found that the monsoon is strong all over India when the snow cover in the Himalayas and Tibet was light, and weak when the snow cover was heavy. Scientists have known for long that the temperature gradient between the equator and the Himalayan latitudes, which goes from warm to cool, reverses when the monsoon builds up. Through June, July and August, the temperature at the Tibetan plateau is higher than at the equator. It is this difference in temperature that is believed to induce the monsoon winds. The extent of this temperature gradient, however, depends on the depth of the snow cover on the Eurasian landmass. When the snow cover is heavy, the temperature does not rise as much as if the snow cover had been light. Once we know all this, the critical positioning of the Himalaya as a determining factor of our weather can be more easily understood. Changes taking place in the Himalayan environment will have permanent and long-term effects that will affect everybody's lifestyle, not just the poor mountain villager whose immediate environment is being despoiled. There are now definite indications of permanent and near-permanent changes on climate in several parts of the Himalayas. Desertification, retreating glaciers, dried up springs, erratic rainfall patterns, and higher summer temperatures. This will be borne out by anybody who went to a hill station 10 years ago and went again this summer. An analysis of temperature and rainfall data for Shimla and Darjeeling for the greater part of this century backs up these conclusions. In both Darjeeling and Shimla, two periods of changing trends are visible, one around 1920-30 and the other around 1960-65. Both coincide with large-scale developmental activities. In the years from 1900 to 1920, average maximum temperature in the summer months in Shimla was 19.4 degrees centigrade. By the 1960s, this had risen to 22.4 and 24.3 in the early 80s. Snow depth reduced from 7 to 10 feet to barely 3 feet in the same period. Mandi used to get snow every 5 years or so, but it has now not snowed there since 1975. On the other hand, intensity and frequency of hailstorms has increased over the entire lower Himalayan belt in the west. Higher up in the realm of permafrost, the mighty glaciers have also been affected. Himalayan glaciers have been steadily shrinking this century. Simply, it means that more ice melts in the summer than is replenished in the winter months. The Gangotri Glacier is shrinking at the rate of 14 meters every year, and the Siachen at an astonishing 31 meters every year. You don't need to be a mathematician to figure out that at the rate they are going, the vanishing of the Himalayan glaciers is not a matter of geological time, but a mere 2,500 years or so. Large areas of the central and Nepal Himalaya are well on their way to becoming near deserts. Soon, they may become like rocky barren terrain of the Afghan hills, once clothed in rich forests.